All right, we got about 4 more minutes before the class starts. If anyone has any question, you can post it in today's text channel, or you can direct message me. Either way works fine. But otherwise, good morning. And this is the only class, or the only lecture for this week, because Thursday is Veterans Day, so we have Thursday off, which is actually terrible for us because that means the next time we're going to meet is going to be next Tuesday. The material that we are learning at this point kind of require the continuity that as much as possible, and missing one class, having to meet next Tuesday, I think it's not going to help. I know some people welcome the holiday because you can do something else on that day, but at the same time, it's not exactly good for this class. Maybe for other classes, but for this one, not going to be not helpful. I cannot do that, Perry. As much as I want to, if I did that, I can get into trouble because the assumption is if it is a college holiday, now I can still be online. Okay, I suppose I can record something and do something live, but I cannot require attendance. So that's kind of the deal. Yeah, we can do that. What Jonathan W said, is definitely doable. Is I can give you some activities to do, and I think I can give you something. I'll recommend something at the end of today's lecture. Yeah, that's a good idea. That is true. Richard is true. What Richard said is true about using a day to kind of catch up and then read forward. But I think for some people, they don't need the extra contact time, and then for some people, having the extra contact time can be helpful. I can do some recording, so this way it's not going to be mandatory, guaranteed. I'm not going to take a role. There won't be anything that would be adding to your score. So missing those activities on Thursday is not going to make a difference. I think that is the most important part of whatever I do, whatever I arrange on Thursday cannot negatively impact people who decide I don't want to be. I have other things to do, which I understand. So that's probably what I can do. So more ungraded assignments. And I'll try to assign those today by the end of today, just so that I don't forget to do it. Yeah, the thing is, even though I would like to continue to teach the class on Thursday, there are people around me who assume that I would be free on Thursday and have already arranged activities for me to participate. And let's just say that's mandatory. It is not optional. So that's why I need to plan ahead of time and get things ready. All right, so we are starting the class now. Okay. All right, so first thing first, a few things that that may be slightly uncomfortable for us to talk about, but I think it is important to talk about it before it is too late. So I'm gonna go scroll all the way back and talk a little bit about academic dishonesty. So these actions, can basically be count to academic dishonesty. Communicating with a live person other than a professor during the exam is not a good idea. Okay, just think about a face-to-face class or on-the-ground class. In an exam, I think it's not a very good idea for someone to talk to another person, even if it is just kind of casual chit chat during an exam, because the professor cannot tell, right? The professor only sees, oh, okay, those two people are kind of chatting with each other. They might be just talking about the weather. Okay, darn it, I forgot to bring my umbrella. It's going to rain today. Well, I got an extra umbrella in my bag. You can borrow it. Oh, thank you so much. Yeah, but the professor cannot tell, right? The professor can only see that, okay, these two people may be collaborating during an exam. So, not a good idea. The sharing of any exam question material before I say it is okay to share is also not a good idea, because you do not know, who has taken the test and who has not taken the test. Some people may have reasons that I have to say, okay, fine, you can take the test a little bit later, or you have extension of time. That's a DSPS accommodation. So if you're not really sure whether the other person is done with the exam, just assume it is not the case. Okay, it's just not a very good idea to share any exam material before I say it is okay to do so. The third one is pretty clear cut. Okay, asking for help during an exam, not only is it communicating with other people. Now, it doesn't automatically constitute communicating, because communication is usually considered two-way, but soliciting help is by itself, an act of academic dishonesty, because it is an attempt to show a level of proficiency that person does not have. Okay, so by that alone, it is already an act of academic dishonesty. Answering solicited help, I understand a lot of people really want to help out, fellow classmates. I get that. Okay, even though I'm not one of those, really friendly and warm people, I know there are such people. Okay, some people really just want to help out a fellow student, but the assessment, the exam, is supposed to be individual. So whatever grade a person is getting, should reflect the competency, the knowledge of that person and that person alone. So I would. It's really constituting academic dishonesty, but I understand the mentality behind people who say, okay, I'll tell you what this is. Okay, but that's actually it's a very high risk to the person who's offering the help, unfortunately. So I'm going to move on. If you guys have any comments you want to add, you can put those into the text channel, or you can participate using the voice channel. It's fine. This is not just me. It's not just a one-way kind of lecture. Because I know that's exactly what it sounds like. Study groups are great ideas. Okay, I have seen very successful study groups. There are a few semesters, okay, on the ground. I have seen groups where everybody participates. There are people who are more outgoing, so those people would be just kind of blurting out possible ideas, okay? And then there are people who are more introverted, and they are more reflective, and they take in, all of those, alternative interpretations of stuff, and then just go like, I think this one may be the correct one. Those other ones, I think that's not what the paragraph meant. So it's great, okay, when you have people who are all participating and have different types of personalities, and they bring different things to the table. However, it only works well when all members of a group put in effort, because I have also seen study groups or groups of people working on the labs. This is back in the face-to-face time, where some people just kind of look over the shoulder of other people and go like, okay, so what did you get? And I'm just going to copy your answer, only to find out that the questions are individualized, and go like, how come mine is wrong? Well, I wonder, right? So for study groups to be successful, you kind of need everybody to be contributing. I'll just, I'm not gonna tell you these, long stories of, how I have seen team dynamics when I was teaching as an adjunct for a micro mouse, which is a robot design and implementation class. It's really fun. It's a year-round class, so it's a project-based class. It was a lot of fun to teach. But from that experience, I have learned that in some groups, in some group dynamics, like a group of 5 people, one person carries all the weight. Okay, the other four are just they're just coasting. Okay, they don't even show up sometimes. So I have a problem with those groups, especially those people who do not show up. Which one was I? I was the loner. What do you guys expect? I was the one-man team. I was teaching the micro mouse class, by the way, but I did have projects back in graduate school and also undergraduate that were supposed to be group projects, and I was the loner. I just go like, I think I can depend on myself the most, and then nobody wanted to team up with me because I was the I was the pimpled young kid in the class who doesn't seem to know anything. So, no one actually bothered to team up with me, which is actually great for me, because I really don't want to team up with other people. Yeah, that's the kind of person that I am. All right, so getting back to study groups. So participants of study groups, to avoid getting implicated because of some members in a group, do not participate in group chats during an exam. Okay, I don't care whether the group chat is done by text, whether it's done by Discord, whether it's done by Zoom, whether it's done by any other medium. The medium doesn't concern me at all. Okay, it is just that if I see any evidence in the answers or otherwise of people sharing the approach of doing things, if I see that it's a little bit beyond reasonable doubt, I would just give those cases to the student conduct officer on campus, and that person who's Chad Funk at this time can sort it out. Okay, I don't want to do this. I mean, but I have to do it. Okay, because that's what I said I would do in the syllabus. So don't get implicated. Okay, I know most people are honest. There are very few people who are dishonest. So don't get yourself implicated because of those few people. Many study group organizers organize study groups at least partially because you want to help out other students. So, and other honest participants have the same mentality. They just want to study together so that everybody will benefit. It is really unfair to these people to be implicated because there are few dishonest members who decide to ignore and break the rules. Okay. If someone breaks the rule, I'm gonna have to do something, okay? Because that's what my syllabus says, okay? I'm gonna do exactly what the syllabus says. I hate to implicate people who are honest, people who really just want to help out other fellow students. But if I see that there's no alternative, then that's what I have to do. So I'm just telling you guys all of this because I think it is important to understand all of this stuff here. All right, so that's my dad mode lecture. It's done. So now we can get back to exam 2 if there are any questions about exam 2, which happened last Thursday. If I don't see anyone wanting to go over, we can go. Oh, okay. Exam 2, question 2. Have the answer posted via Google Docs share. Okay, I can do that. I guess I haven't run the script yet to share your own answers along with the answer to your specific questions. So let me find that tab first. Got it. All right. So let me do that right now. I can do a share. Alright, so I'm running it right now. You will probably see that your exam is being shared back to you as commenter. So as a commenter, you can go back and actually suggest changes. Don't do that, okay? Because I can tell, okay? In the past, some people have done it in the past. They go back to the exam and then suggest changes according to the key. Yeah, it doesn't actually go in. It only appears as suggested changes. And I'm also sharing a key to your specific questions, so you can actually take a look at what the answer is supposed to be, and you can compare that to your own answer. It doesn't really tell you what score you're going to get, okay, because it's not an automatic grading mechanism, but it does give you an idea of what is the correct answer. So it should be being done right now. I can see the script is running. All right, so I'll let it run over there. And then the next question is it possible to get partial credit for a question even if the answer is incorrect? So it depends on how much work is shown. Okay, if enough work is shown, the line of reasoning is okay, and it is because of an omission, a minor error, that the final answer is wrong, then partial credit can be given in those cases. There we go. Oh, okay, so I need to change my script. So I'm going to let it run through the first time, and then I will change the script to handle exam 2 and then run it again. Thank you for letting me know. All right, so for exam 2, yeah, so I got it. I got that you guys are getting a reshare from exam 1, so I'm going to reshare again with exam 2. Just give me a second for this script to complete first. What does partial credit look like? Well, it all depends, right? It depends on how much is shown by the partially correct answer. So it kind of depends on that part. The syllabus tells you what a 4 means. A 4 over 4 is an A, okay? Because 4 is the GPA of an A. That basically means, oh, I need to give you guys the road taking activity right now. So hold that thought. Hold that thought. And okay, so what is the time right now? It's already 12. I'm going to adjust the end time, the due date, or the due time to 22. Give me a second here so you guys won't see it yet. There we go. Save and publish. And you should see, you can use the search feature of your browser and look for 20211109, and then the word is flatten. So I'm typing it in the text channel, copy and paste it, and you should be done. Yep, road taking activity is already published. So look for 2021 road taking. I can post that link here too. Good job, Richard. Good job. Oh, Thursday? Nope, I won't be doing road taking on Thursday. Okay, on Thursday, no one is required to be doing anything with this class on Thursday. Okay, I might be posting material, but it is not going to be graded, and I'm not going to take roll. No one is going to lose any point if they just say, I'm going to sleep the entire day on Thursday. No problem. Okay, not a problem. So there we go. Okay, road taking activity being done. And we're getting back to exam 2. Okay, my script is completed. So let me change my script a little bit. I have to change one variable name to make it do the same thing with exam 2. So let me change that first. I should probably use a better approach to do this, maybe by date or something like that. There we go, and there we go. Okay, so now it should be working to reshare, not reshare, this is new, so it should be sharing your own exam back to you as a commenter, and also sharing the key that is specific to your set of questions. So there we go. I think it is working. Looks like it's working. All right, so unless people have any specific questions about exam 2, because the format of exam 2 is very, very close to the practice exam, so I'm just gonna not talk about exam 2 unless there are people who specifically say I want to talk about something on exam 2. All right, I'm not seeing anything. Oh, okay, Colton is typing. And Richard is typing too. Cool. All right. Okay, I can do that. I actually came prepared. Yeah. All right. So here's the actual exam. Question number one is interesting because um, I when I wrote this exam, I was thinking the NOR symbol was already introduced. Okay, when we talked about the ALU, the NOR gate was specifically talked about that it is a negated OR and it implements um, the Z flag. Okay, the Z flag inside the ALU was implemented using the NOR gate. But then I thought about it a little bit more and go like, maybe some people don't remember that, right? I mean, yes, okay. So what I did was in the text channel of that day, I specifically explained it, okay, in here. I said, oh, in Q1, there are NOR gates, the ones with a bubble, and they are not NAND gates. A NOR gate is a negated OR, meaning the output is the negation of in 0 or in 1. So there we go. So it's actually explained, okay. Not only is it mentioned in class, okay, it is also explained in the chat channel of the exam on that day. So knowing that, okay, so I'm gonna work on this one. I'm not sure how detailed you want it to be, okay, because I can just also just post the key to my own set of questions, because that's going to be, it's machine generated, so that's why it's a very tedious way to do it. So I start with the input ports. Okay, the input ports are 0, 0, 1 in my case, and then the so-called iteration is basically each propagational delay. Okay, so each propagation is one iteration. So in the first propagation, the AND gate is going to update. X is now going to output 0 because input is 0, 0 for device X, and then for device Y, it is also going to output 0 because one of the input is a 0 and the other one is a 1. So now we know X is outputting a 0, Y is outputting a 0 as well. Those two zeros are connected, if we go back to the diagram, so they're connected to one of the inputs of the NOR gates, okay, one with V and one with W. However, because with a NOR gate, if the other pin is unknown and we only know one of the pins is a 0, it cannot tell you anything about the output. So that's why we have to come to the conclusion that both of the NOR gates is going to output something that is unknown. So that would be the end of part 1. With part 2, port B becomes a 1. It was a 0. Now it is a 1. And because of that, X is continuing to output a 0 because the input of X is 0, 1 in this case. However, Y is now going to output a 1 because the inputs are 1, 1. So when you see the bold phase now, it means it is a transition. It is an output being changed. Now, in my automatically generated answer, it does not do the node spreading of a value over the nodes. So that part is actually implicit in the automatically generated answer. I can modify the script to also output that. But the bottom line is when Y is outputting a 1, that changes the input of W. And as a result, W is going to output a 0 because one of its input is a 1. And because W is a NOR gate, which means if at least one input is a 1, the output is going to be a 0. So that's why W is now changing its output to become a 1. But W's output is also going back to V, and as a result, V is also going to get updated. And V is going to output a 1 for sure because both of its inputs are zeros. And V is going to output to, oh, by the way, W's output is going to Q, so Q is getting a 0. And then V's output is going to P, so P becomes a 1, and so on. So I'm not really sure how detailed you want me to go into, or whether you want me to continue with the other steps. But basically, that's how it goes. So if this is okay with you, I'm going to stop here, because you will get your own key to your specific question. Because everybody, well, I shouldn't say everybody, but there are, I think there are 8 variations of this question. So, so depending on which variation you get, the answer in the automated generated answer is always correct. That is specific to the question that you are getting. So you just have to know how to read the key from the automated generated answer. Alright, so Omar is typing something, and while he's typing something, I'm going to skip to question number 3. So, question number 3. My specific question is there's a value of 1 times 1.109375 times 2 to the power of 10. The reason why I spelled it out in English is because this document is generated using just as an HTML, so it's not getting through LaTeX, to convert the LaTeX, equations into the proper mathematical notation. So I just kind of spelled it out using words. The questions look different for Q1 than what we did in class. That's just the format, Omar. That's just the format. This is machine generated, so it doesn't include the node, the spreading of a value through the nodes. It is implicit in this case. It only reflects propagation changes due to devices, due to the input of a device changing. The output is getting changed. So it's kind of like a shorthand compared to what we talked about in class. But that's what I was doing exactly, was to tell you how to read the key of the file that is shared with you. Alright, so getting back to question number 3. So read the question carefully, okay? A bunch of people did not, okay, unfortunately. Now, whether those people, kind of talk to each other and they kind of share how they looked at each question, I do not know, okay? All I can tell is they were all incorrectly interpreting the questions. So the question, okay, let me go back to the question first. So the question is saying a 64-bit, which is basically a sequence of 64 binary digits, represent a value V1, and V1 is exactly what we saw in the key, using the correct IEEE double precision floating point number interpretation. And I even not boldface, but I even italicize correct. So, and a bunch of people say that assume this is using the incorrect double precision floating point number format, and they use the wrong number of bits for the exponent. I don't know what to say. I really don't. So in that case, okay, the first thing we need to do is to say, okay, how do we convert this into a binary number? And then a bunch of people again, just gave me, something like, oh, 1.109375 is exactly this number in binary. How, right? The question did ask, show all steps. Okay, so without those steps, points will be deducted. Okay, now there are many ways to show me those steps. Okay, you can either use a table. Okay, use a table like this and show that, okay, now that we know all the powers of 2, power 2 to the power of -1 all the way to -7, I figure that this sum here, okay, this value over here is it has a 2 to the power of -4, it has a 2 to the power of -5, and it has a 2 to the power of -6. Okay, so as long as I see how someone understands the process, okay, I will give full credit. At the same time, if somebody just gave me this number here in base 10 equals to this number in base 2, I don't see how it is converted. Okay, and if I don't see how it's converted, it is not step by step, and if it's not step by step, then there won't be full credit given in that case. All right. So after that, what do we do? Well, we already know what is the power of 2 because as a part of the question, this is 2 to the power of 10. The question is, what is the bias, right? How many bits are we using to represent the power of 2, and what is the bias in that case? Because we are dealing with the first part of the question, which is using the correct IEEE double precision floating point number, so that means we are using 11 bits to represent the power of 2, and the bias is 1023. So that's why I'm adding 10 to 1023, which is 1033. And then I also have to show, how to convert 1033 into its binary representation. So in this case, we have 2 to the power of 10. We have 1 to the power of 1 of 2 to the power of 3, and we have 1 of 2 to the power of 0, and that's why all of those bit positions are ones, and then the rest are all zeros. Since the value is non-negative, the sign bit is 0, so now we can string everything together. So we got the sign bit, we got the biased exponent using 11 bits because this is using the correct IEEE double precision floating point number, and then we have the fractional part of the mantissa, and just basically extending it, a whole bunch of zeros all the way until we use up all 64 bits. Oh, well, I did talk about base conversion. So, I mean, step by step means you have to tell me how you got a value. So if you say I go to this website and it did the conversion for me, and this is why I got the answer, well, maybe that's what you need to write, is to tell me that, yep, I went to a particular website and the conversion is automatic. Yeah, we can do that. And then for the second part, the bit pattern is now interpreted using the erroneous way, which is, in this case, I think it's using 9 bits for the exponent. So now we are using exactly the same bit pattern as it is here, except this time we break it up differently. So the first bit, or the most significant bit, is still the sign bit, but then we only use the next 9 bits. Let's see. Okay, we only use these 9 bits to represent the exponent. So with 9 bit for the exponent, the bias is 255. So I think I actually selected the wrong number of bits. And uh-oh, that doesn't look right. Oh, okay, never mind. I should be looking at this part here. Okay, so this is the biased exponent in binary, and that converts to 258. And because the bias is 255, that means the actual exponent is just 3. And then the rest of this, okay, starting from here and all the way to the end or to bit 0, that's the fractional part of the mantissa. As a result, the mantissa is 1.010000111 in base 2, and once we convert it using base conversion, we get a value of 1.2773435, and as a result, the interpreted value based on the erroneous format is what basically is 10.21875. So there we go. Question number 2. Okay, somebody asked for question number 2. The exponent was 11 bits. Yes, that would be the correct number of bits for the exponent when you're using the correct IEEE double precision format. So that's for part 1. We use 11 bits for part 1, and then we use 9 bits for part 2. In other words, I flipped the order of the questions, okay? Because in the practice test, I basically gave you the wrong interpretation first, and then ask you under the correct interpretation what is the value being represented. So in this test, I just reversed the order. I gave you the correct one, and then ask you under the wrong interpretation what is it going to be. Okay, so for question number 2, specific to this question here, let's see. Okay, so we're basically, for the first part, we are looking for something that is updated. So typically it means something has a 1 in it. So even though RAM cell is a 1, we can see RAM load is also a 1, which means RAM is not getting updated. Let's see what is getting updated here. RIEN. Okay, so RIEN is a 1. That tells me one of the 4 registers inside the register bank is getting updated. Which one is updated it depends on the select. So we know register A inside the register bank is getting updated. And then we also see D0 of ROM is a 1, so that means the instruction register is also getting updated. So that would be the first part, and in the key it indicates so as well. Reg A is updated because RIEN is a 1 and RI cell is a 0. PC is updated because PCEN is a 1. Oh, okay, I did not see that. Okay, that's that's me being careless. So PCEN is a 1, so PC is also getting updated. So those two are updated, and I think instruction register is also getting updated because of that. Next, identify how these components are updated. For each component that is going to be updated, identify how it is going to be updated. Column C of the opcode table is an example of what this part should look like, and explain why you think this is how it's going to be updated. Hint, how the multiplexers, demultiplexers, and possibly other components are configured by the various bits coming out of ROM are listed in the pre-dissected microcode slice. Phew. Okay, so that goes back to kind of what I put here. This is actually automatically generated. PCMux is a 0 because PCMux is 5 or 6. PC Inc is a 1 because PCMux is 5, 6, or 7. PC is incremented by 1 because address mux is a 1, and PC Inc, because of that, PC Inc is a 1. PC.Q connects to RAM.A because address mux is 1. RAM is being read because RAM cell is a 1 and RAM load is a 1. So that basically the bottom line is the PC is getting updated by whatever the PC is pointing to. And on top of that, register A is also getting updated by... Oh, no, I take it back. In this case, the program counter is incremented only by 1, so PC is incremented. And then register A is connecting to the D port of RAM, so register A is getting whatever PC is pointing to. And as a result, the instruction is the LDI instruction. And then for part 4, because we're using register A, so the actual bit pattern for the opcode is 6C in hexadecimal. Alright, so I'm going to go catch up with the text channel stuff. Okay. For the hexadecimal opcode for the instruction, I forgot to put in the 0x. Nope. There will not be any markdown because, well, just because, if it looks like a opcode in hexadecimal, I'm going to assume it is in hexadecimal. There we go. I'm not sure whether, it depends on which question. For some questions, there are, each person is guaranteed to have, that person's own question. And then for some of the other questions, there are not enough variations for everybody in the class. So there might be people having the same kind of question. Yep. All right. So I'll be good with exam 2. All right. Very good. Okay. So I am not trying to rush. However, we do have to go over the material that we need to talk about today so that you can continue with the lab today. So I'm skipping the compiling part just for a little bit, and instead we'll talk about the calling and returning from subroutines. Now those two topics, how do we deal with conditional statements and loops and whatnot, is orthogonal compared to how we are calling and returning from subroutines. Orthogonal means they are fairly independent. I can talk about these two topics in any order and it wouldn't interfere with each other. So we'll talk about calling and returning from subroutines, and we are starting with a program like this one, where you look at this program, go like, this program is pretty meaningless. Okay, I think most of you would agree that this program is really kind of meaningless because it doesn't do any processing. It doesn't have any input, doesn't have any output. It's not even entertaining in the least bit. However, it is interesting for us because it shows us what needs to be done when you are calling a subroutine. Okay, this is seen from the perspective of a C program. Okay, we are not even getting into assembly language programming. So when you look at this as a C program and you look at the behavior of this program, it's pretty easy to understand. We call F, okay, because main is called implicitly by what we call the startup code of a program. So C is actually called as just as any other function. So when main is called as if it is just any other function, it's just the first function to be called within your entire program. It's the entry point of your entire program. So main says, okay, I need to call F first, okay, and then we get into F. F doesn't do a single thing, returns nothing, and it's done. So when F is done, it's going to continue execution with this line in main. And then this is going to say, okay, we're going to call F again, even though it is useless, we're going to call it again. So we call F. F goes like, I got nothing to do, I'm going to get back to the caller. But this time when F gets back to the caller, it is getting back to the return statement. That is the tricky part, okay? The tricky part is depending on where F is called, where it needs to go back to is different. So we cannot just use a Jmpa because a Jmpa is static. Okay, when you specify a Jmpa instruction, the immediate, okay, where you say, okay, this is where you need to go to continue execution, that is static. It doesn't change. Okay, so we cannot use a Jmpa to go back from a called subroutine to the caller. That doesn't work. Now, going from the caller to the callee, we can use a Jmpa instruction. It's okay in that case because when we specify, let's go ahead and call F, okay, we are just continuing execution at F, right? So a Jmpa is fine because every time you call F, you're going to have the same destination. You're continuing execution at exactly the same place. So Jmpa is fine. But getting back from the callee to the caller is the tricky part. So what we're going to do is we are now going to digress and talk about a stack. Okay, if you have taken CISP310 already, you know the abstract data type or the class of stack. But if you have not, it's okay. Okay, we'll talk about the Lifo structure right now. Lifo means last in, first out. Okay, so in computer science, there are two main ways of arranging things, of storing and then retrieving things. One is Lifo and the other one is FIFO. FIFO is first in, first out. Lifo is last in, first out. So when you're in a line, let's say at Costco, to pay for your stuff, it is a FIFO, or we certainly hope it is a FIFO, first in, first out. Okay, but when you are loading up a U-Haul truck, it is Lifo. The very last item that you push onto the truck before you slam the tailgate down is going to be the first thing to fall out of the truck when you open up the tailgate. So it's last in, first out in that case. So the way we're going to implement last in, first out in at a low level is we'll start with certain definitions. The first one is not really exactly useful. All it does is to tell us, okay, how big of a stack are we talking about? 32 items. And then the second one is declaring the stack itself. In other words, we are actually allocating for the space that we need, for the stack. Okay, so we are saying, okay, these 32 bytes in RAM is now the stack. Okay, the stack that we are going to use. What is most interesting is now we have a stack pointer. SP is the abbreviation of stack pointer. So the stack pointer has a few rules applied to the stack pointer. So the stack pointer points to the last thing that we save on the stack. Okay, so just think about you're loading up a U-Haul truck. Okay, so you threw a box, okay, of books onto the truck. That's storing something into a stack. When you're retrieving something, taking an item out of the U-Haul truck, that's retrieving item from the truck. So there are two operations you can do with a U-Haul truck with a stack. One is to store items into it, and then the other one is to retrieve items from it. So now the question is, how are we going to store something into the stack? So these operations here, these two, they're C statements. These two combined is how we store something into the stack. So I know this is counterintuitive because most people say, but don't we want to start from the beginning of the stack? Well, and then I'm going to ask you a question of why not from the end? Okay, there's no intrinsic reason why we have to start from the beginning of an array and not starting from the end of an array when we want to utilize the content of an array. So in this case, we're using the counterintuitive way of saying, let's start from the end, okay? The byte that has the highest address on the stack. We're going to store items at the very end first. But that means, the stack pointer, which is pointing to the last item that has an item stored, it first has to be decremented, because before the decrement, the stack pointer is already pointing to the last item that we have stored on the stack. So we don't want to overwrite whatever was already stored on the stack. So the first thing we need to do is to decrement the stack pointer and say, okay, since this location, which is what the stack pointer is currently pointing to, is already storing something, I'm going to have to move the stack pointer down by 1 byte, so that that 1 byte which was not previously pointed to by the stack pointer can now store the value x, whatever x is, into that space. Alright, so I'm just going to pause here and see if there are any questions about this particular stack operation, how we push an item onto the stack. The term push simply means we are storing something. Okay, it's technical to the discussion of a stack. So x is the value that we want to save on the stack. It's just a value to be saved. Okay, alright. So x can be a lot of things. Okay, x can be just a number that you need to somehow, or for whatever strange reason, you need to save on the stack and then retrieve it later on. Can be an address of a place, can be simply a value, because we only got 4 registers, right? So eventually you're going to run out of registers to store temporary values. So one thing we can use the stack for is to store temporary values that you might need to use later on, because you only got 4 registers. Alright, so any other questions about these two operations? How we allocate for 1 byte and then we store whatever value x that we want to store at the location that we have just allocated. All right. All right. So you don't need to use a semicolon for storing. Yeah, I really should have a semicolon over here if this is C code. Colton is correct about that. Let me so why don't I fix that when you guys continue to kind of think about whether you have a question about just these two statements, imagining there is a semicolon over here. And this is module 304. Alright, so the question is, when SP is decremented, does it just point to a new space, or does it move the last element stored as well? We are just moving the pointer. We are not moving what it points to. So this operation here does not change anything that the stack pointer is pointing to. It simply changes the pointer itself. Think of a pointer as a bookmark, and the pages are the locations. So when you're moving a bookmark from one page to another page, does it change the content in the pages? So that's one way to look at it. Where does the stack pointer points to? Well, we'll address that later. Okay, it's actually right here, but we'll talk about that later. So let's just assume that the stack is already in operation. Okay, so we already got some stuff stored on the stack. This is how we store something new on the stack. And I'm just refreshing the page because I just updated the code to include line numbers and also the extra semicolon. There we go. All right. All right, next is how do we retrieve something from the stack? Okay, now that we might have stored something on the stack, how do we retrieve those items? So to retrieve, the first thing you do is to say, hey, stack pointer, tell me tell me the content of whatever you're pointing at right now. Because that's part of the rule, right? The rule is the stack pointer always points to the last thing that you stored on the stack. So all you have to do is to dereference the stack pointer, and then whatever value is coming back from this dereferencing is going to be the value that you is the value that is retrieved. Okay, and you usually want to store that to some place. Very occasionally, just go like, I don't care about that. Let's just toss it away. Okay, very seldom. Okay, but most of the time you want to retrieve it and then put it back into a place. Typically, in assembly language programming, it's going to be one of the registers. But after this operation, you are done with that item. So you need to deallocate the location that was used by that item by incrementing the stack pointer. So if decrementing the stack pointer is to reserve a byte on the stack to store something new, then after you retrieve the value of something that you have previously stored on the stack, incrementing the stack pointer is how you quote unquote deallocate that byte and say, hey, this byte is now free to store something new again. That's basically what the stack pointer is doing. Okay, whatever the stack pointer is pointing to and everything above that location, they are in use on the stack. Everything that is below where the stack pointer points to is free and they can be used, to store additional items. That is how the stack is going to be used. So the next item here is to talk about how do we initialize the stack pointer then. So you can see how the stack pointer is initialized to the address of 1 byte past the end of the array. Because the array has exactly stack size number of items, and this is pointer arithmetic. Okay, so pointer arithmetic like this is really doing the same thing as the address of stack and then open square bracket, stack size, close square bracket. So any C programmer will tell us and say, but that element does not exist because the index of the last element is going to be stack size -1. So if I use stack size as the index, I'm actually referring to an item that does not exist, that is not allocated on the stack. It's 1 byte past the end of the stack. But that's exactly where we need the stack pointer to be, because for the very first item to push on the stack, guess what? The first thing we do is to decrement the stack pointer. So that means if this is how we initialize the stack pointer, by the time we have the dereference to store something onto the stack, we would actually be utilizing the very last location, legitimate location of the stack. Does everybody see how the initialization, which is this particular statement, works well with how we store items on the stack? We actually utilize every single byte on the stack this way. If I were to initialize the stack pointer to stack plus stack size -1, then the very last location on stack would be unused. It's impossible to use that location if I did that initialization. Alright, so we got Richard and Jonathan typing. Alright, so I'm going to scroll. Well, maybe I'll just wait a little bit before. All right, so we got the first question. So just to keep track of things numerically, stack is as a number is 0 and stack size is 32. Nope, stack itself is declared here. So stack itself is an array, and it has stack size. This is the number of elements in the stack. Each element is an unsigned 8-bit integer, which is basically just a byte. I mean, you can actually put this code into online GDB. So if I have extra time, I would do a little demonstration. Everything is going to be in C, but it will still be a useful demonstration to show you guys, what we can do with the stack. So is the pointing out of index at 32? Yes, it would be. In other words, what Ivan is talking about is after we do this initialization, SP itself as a pointer will be pointing outside of the area of RAM that is allocated to stack. That would be correct. However, if this is how we store something onto the stack, if this is how we push items onto the stack, by the time we actually utilize the value of the stack pointer to store something, it would be legitimate again, because the very first thing we do is to decrement the pointer by 1. So that would get us back into the actual region where we have the allocation for stack as an array as a variable. Okay, I look at C as a subset of C++. So the concept is this is also in C++. In other words, all of the same thing here, they also exist in C++. So yes, I do know most of you did not take a class in C, instead you took a class in C++, but because C++ is a superset, which means everything in C is also in C++, so this is using just the portion that is C, and it is not using the portion that is specific to C++. So thank you for the reminder, Maddie. I do understand that. Now, whether your CISP360 class got to pointers, now that is a different question. And I cannot answer that question because it depends on from whom you took CISP360. All right. Well, we don't. That's the thing. So Perry, asked a very, very good question: is how can we tell whether it is out of index? The answer is not something that we want to hear. La 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 la. It's because we don't actually check. So we can be pointing out of index, pointing out of the region of the stack, and not know about it, and then bad things will happen. So, but that's a very good question, Perry. And then Lisa asked, mine did not because I took it in the summer. Well, then we have a little bit of a problem, don't we? Now, I'm not saying the problem belong to the person who took the class, but we have a problematic situation in if that was the case. So let me sign in to something that you guys don't have access to, but it is necessary for me to get to this part. Okay, I'm getting to... Okay, what I'm doing on the side, which you cannot see, is getting to the curriculum of CISP360, which will tell you what topics the class is supposed to go over. And I understand that is not going to help, okay? Just because it is supposed to be covered and somebody decided not to do it, it's not going to help. It's not going to help you as a student in this class. However, it is important for us to understand this, so this way, possibly, maybe, you can give some feedback to the department or the professor who taught that class and say that, hey, we're supposed to go over these things that is actually necessary for the next class. So if those concepts were not covered, it would not be good. Alright, so I'm just going to look for the word pointer. So these are the topics that should be covered in CISP360, and this is the syllabus, not syllabus, this is the curriculum specific to ARC, but I would suspect the same topics are also in the curricula of the 3 other campuses. So pointers is actually one of the topics, and it is even though it's close to the end, it is not exactly at the end of the entire class. So pointers to primitive types, structures, and arrays, and passing by reference, what is dereferencing, pointers, and so on. Those really should be covered in CISP 360. So having said that, I will kind of let you guys think about it a little bit, and in terms of how we want to proceed at this point, because we definitely need to use the concept of a pointer. In a way, yes. In a way, no. Okay, because when we translate all of these into assembly language constructs, then you go like, oh, okay, so it's the same thing as an ST instruction, which we have talked about. And then when you look into how an ST instruction works in terms of what kind of pathway it needs inside the processor, you go like, oh, okay, I get that part. Okay, we just need to have one register to connect to the A port of RAM. We need another register to connect to the D port of RAM, and then RAM is going to be either in reading mode when we are doing something like this, or RAM needs to be in writing mode if we're doing something like this, and that's how we do it in the processor. So in a certain way, this class can actually reverse the whole thing and actually say, if you did not understand what is a pointer and what is dereference, I will explain to you the lowest level mechanism of what a pointer is and how dereference works. So it might be able to work that way too. I'm not 100% sure. Okay. All right. Okay. Well, thank you, Lisa. I'm not trying to put this on you because you did not decide how much material to cover when you took that class. It is up to the professor who did it. So an address. Perry is correct, almost correct. An address is okay. An address in C++ is an address in RAM. So what a pointer is something that can change. Okay, so what a pointer is the content of the pointer can be used as an address of RAM. So I can say can be because that's not all the time. All right, I'm just looking at the time here. I think I have enough time to go over also calling and returning. So the first thing before we go any further, okay, the first thing is to look at these constructs here and find out, okay, how do we do this in assembly language? So what I'm going to do is I am going to use mousepad on the side. I'm not going to use Joplin because Joplin doesn't really help in this case because we are just talking about raw code here. So the first thing is register D is SP. Okay, and somebody may ask, but why register D? Okay, I'm going to answer that question right away and say it is arbitrary. Okay, I just say let's just use register D as the stack pointer for the processor that we have. Okay, so that is completely arbitrary. There's no reason why register C or register B or register A cannot be the stack pointer. I'm just designating register D as the stack pointer. All right. Oh, okay, gotcha. And that's because of my phase 2. So we'll put here. There we go. All right. So register D is the stack pointer. So now that we know register D and SP are synonymous, how do we decrement register D? How do we perform SP minus minus? So SP minus minus is translating to what in assembly code? You can go through the opcode table. Yep, decrement D, that's right. All right, so this is done by decrement D. Okay, the next one, which is we are storing something to what the stack to the stack. Let's just say x is a value that is currently in register A. Okay, so I will make it clear that we are making an assumption here. So we'll say register A has the value that we want to save on the stack. So when we try to perform this operation in C++, what are we trying to? How can we do this in assembly language? We are trying to store a value that is currently in register A to where the stack pointer is pointing to, but the stack pointer is really just register D. So how do we do this? I mentioned that instruction just moments ago. Yep, very good. Okay, you guys are all correct. Okay, STDA. There we go. Oh, okay, so maybe it's not too bad at this point. Okay. All right, so what about popping something from the stack? So this is what we need to do. And once again, we are making an assumption, and we say register A will contain the value popped from the stack. Okay, so that's just an assumption, but based on that assumption, how do we perform this operation? Go to the location in RAM that the stack pointer is pointing to, and whatever value is being stored at that location in RAM, we want to retrieve it and then store that in register A because we have designated register A to store the popped value or whatever value we are retrieving from the stack. Yep. Okay, very good. You guys are all correct. Nice. Well done. And then the next operation is SP++ because whatever location that we took the value from is no longer useful anymore, so it should be available again. Yep, there we go. Good job. Okay, so you guys are getting it. Very good. So that means, hey, maybe it's not really that bad because to push something on the stack, we just have to decrement the stack pointer and then store something into the location that we have just allocated. And then to retrieve something from the stack, we have to designate a register to store whatever value we want to retrieve from the stack. But once we have decided which register, then it's just an LD instruction followed by an increment instruction. So how do we initialize the stack pointer? Okay, so now we are talking about how to initialize the stack pointer. Well, that's a very tricky question because we are not in a C programming environment, so we cannot just declare and say, hey, this region of RAM is the stack. But we do know one thing: the instructions, they go from location 0, and then each instruction is just right after the previous instruction when we are assembling. So instructions go from location 0 to higher addresses. So what we'll do is we will do what most people have done in the past. Okay, this is nothing new, this is nothing innovative, which is basically saying, let's just assume the stack is at the very end of the memory space and then it goes backwards. In other words, we'll initialize the stack pointer to one bypass the end of RAM, and then it will just kind of grow to lower locations. As we put more items onto the stack pointer is going to decrement. So the way we initialize the stack pointer is kind of interesting because what we are trying to do is to initialize the stack pointer to location 255 because 255 is the very last location of RAM in TTP. But we also want it to be one byte past that, right? So we want to say +1. But then somebody's going to say, but Tech, this is bad because 256 requires 9 bits to represent, and since the stack pointer is register D, which only has 8 bits, how are we going to store 256 into an 8-bit register? What about this? We just initialize the stack pointer to 0 because the first thing we do when we want to store something onto the stack is decrement. When you decrement 0, what do you get? If register D is 0 at this point, and then you execute the decrement D instruction, what do you think is going to be in register D after the decrement? You can answer in base 2, base 16, or base 10. Exactly. So Matty is exactly correct. It's 255. Okay, so it all works out. So the way we initialize the stack pointer is simply to say, let's just put a 0 into register D. Now there are two ways to do it. This is the obvious way to do it, and then this is the not so obvious way to do it. Can everybody see why the second one would actually do the same thing, which is initializing register D to 0? All right. And which one do you think is shorter in terms of the number of bytes it needs? The I requires an extra byte. So it's the sub. Yep. Because in the LDI instruction, it takes 2 bytes. The first byte is the actual opcode, and then the second byte is the immediate value, which is 0 in this case. But the subdd instruction is one single opcode with no immediate value to take up the second to take up an extra byte. So subdd is actually slightly more optimized compared between these two. Subdd is a little bit more optimized. All right. No, not a problem, Perry. No worries, because you kind of have to think like an assembler in order to get to the right answer in this case. All right, so we are almost done here. We got 13 minutes left. So now the question is, how does this relate to calling and returning, right? Because that was what we were about to do, is to implement this code in assembly language. So let's go ahead and implement this in assembly language. So I'm going to open a new tab here. And because I just want to say, okay, what does this code look like in assembly language? I want to preserve the order of the definition of the subroutines of the functions. Okay, so what we'll do is we'll start with a no op instruction, because I do want to run this code in the TTP simulator. So we'll start with a no op instruction, because this way we'll generate a trace, which is going to be very useful if you want to understand what is going on when we run this code in the tax toy processor. So we'll start with no op. The way we implement a function is we just use a label to designate its entry point. So f has an entry point here, and we'll just say, well, we don't quite know how to return from a subroutine yet. Okay, so we'll just say code to return to caller, because I'm not quite sure how to do that yet. Okay, and then we have main, and the main is down here. Main has nothing to do, and then we say code to call f, because we don't quite know how to do it yet. Code to call f, and we cannot have a return 0 from main in TTP, because there's nothing to return to. Your entire program is this particular program, so there's nothing to return to. There's no CLI, there's no command line interface to return to, there's no IDE to return to, there's no integrated development environment to return to. So the best we can do is really just to say, yeah, we'll just kind of stop here. So are we good so far in terms of the overall structure of this code? Okay, very good. So now the first problem we have is no op is just going to say, I got nothing to do, so I'm just going to go forward. Whatever is next to me, let's do that next. Well, that thing next, it turns out to be return to the caller. No, I don't think that's the right thing to do, right? So we need to kind of jump around the other function definition onto main. Okay, because we want to start with main, and which is the entry point of the entire program. Now somebody could also say, and say, Tech, why don't you just move main to the first thing right after no op? Then you don't need to jump around the other function to get to main. Yes, I could have done that. Okay, but if I did that, then I would have changed the ordering of the definition of the functions, which is not what I want to do. I want to preserve the order of the definition of the functions in this case. Okay, just to reduce the number of variables between the C code and the assembly code in this case. All right, so Tag, you did mention something about the call can just use Jmpa, because, to get to the function being called, it is always ending at the same destination. Yep, you're right. I did say that. Okay, so we have this, and then we have this. Then you look at this code and go like, but Tag, that's not going to work, because if I just do a jmpf from main to f, yes, we do end up at f, okay? But then f has nothing to do here, and then it will just kind of fall through back to jmpf, and now we have an infinite loop between the label f1, f colon, and the jmpi to f. This is becoming a very tight, infinite loop. So that's not going to do the trick. What are we going to do here? Well, do we have to save where we need to go before JMPI? That is correct. So Matty is 100% correct here. So now we have to say, okay, part of what we need to do to call F is to say, let's remember where the callee needs to go to continue execution when f returns. Okay, so the callee is actually just f, so I'm just going to replace it with f over here. Does that make sense? Because before I continue execution at f, we kind of have to leave behind a crumb of bread so that the subroutine can say, oh, I see where I'm supposed to go to continue execution. All right. So now we need to say this, and then we go like, but Tag, what does this have anything to do with the stack? Well, we're going to use the stack for this purpose. The stack is going to be used to store crumbs of bread or breadcrumbs so that a subroutine would know where to continue execution in the caller. Okay, so let me see. If we're trying to store something onto the stack, then we automatically say, okay, we need to decrement the stack pointer and then do a store to wherever the stack pointer points to, and we just make a general assumption. Whatever we want to store, the value is going to be in register A. Okay, so we just automatically put this in, and now the question is, how am I going to initialize register A so that it remembers where the subroutine is supposed to go when it returns? And before we go any further, I'm just going to say, okay, let's go ahead and initialize the stack pointer first. Okay, so subdd is initializing the stack pointer. Typically, it is not needed because when you reset the processor, all registers will return to a value of 0 automatically. I'm putting this in here just to explicitly show that we are indeed explicitly initializing the stack pointer, but it's usually not really needed. But to understand the concepts, I'm going to put it here just to be clear. All right, so now the question is, what do I put in register A so that it remembers whatever we save on the stack, remembers where the subroutine is supposed to go to continue execution? Well, how about the label? Okay, what about the label here? And I'm going to use a long label name just so that the label name itself is self-documenting. So I'm going to say first call of f returns here. Oof, that's a long name, but it is pretty self-documenting, don't you think? So what I need to do now is to say, oh, maybe that's just what we need to push on the stack. So we do LDIA with first call of f returns here. Are we good so far? So I did not type the program in a very sequential way because I keep asking the question of, okay, we know this is what we need to do, but if we just do this, we have a problem. So we're going to have to do something else, but that something else is leaving behind a placeholder, and we need to find out what needs to go into the placeholder and so on. So I'm trying to explain it in that way of backward engineering what we need to do. All right, so I'm getting some confirmation in the text channel, and we're going to continue with the code here. So right now, if we read the code sequentially from main, the first thing we do is we initialize the stack pointer. The second thing we do is we are pushing whatever this label is on the stack. So the stack has one item, which is this the value of this label here, which turns out to be the address of this second JMPIF instruction. So now the question is, now that we have pushed that the value of that label on the stack, and then we have an unconditional branch to F, and F says, I got nothing to do, I'm ready to return. How are we going to return? Well, the first thing is, we know that thing is in register A. Whatever we have stored on the stack is in register A. If we just look at this very, very specific program, we can just say, oh, it's in register A, so maybe we just need to do something like this. Except it is incorrect, because register A is not an immediate value. It is a register, so JMPI with A doesn't work. However, there is an alternative. There's a different opcode for just JMP and then with a register. If you look up the opcode table, the operation of JMPA is actually really simple. All it does is to say the program counter gets whatever register A has. And in this case, it would seem to be the right thing to do because register A does have the return address. Now, this has one problem, okay? The problem of using just JMPA in this case is, how do you know register A actually has the return address? And then people would just point to this line over here and say, but tech, line 13 clearly shows that register A has the return address. Right. However, the callee has no idea. It cannot assume anything from the caller. In other words, whatever main does, okay, this entire chunk of code is technically invisible to the callee, to the subroutine. The subroutine and the communication between the subroutine and the caller is very, very specific. They cannot see into each other's definition. So we have to pass A to F. That is correct. And what is the mechanism of passing the value in register A into the function? We cannot assume registers either. Okay, one of the rules between the communication of a callee and a caller is you cannot make assumptions about what is in the registers. In other words, by the time we get to F, we cannot make assumptions of, yeah, we kind of know that main is putting the return address into register A before we get here. No, we cannot make that assumption because, in other words, this entire code is invisible from the perspective of the subroutine. So the subroutine cannot assume anything in registers. The only thing the subroutine can make an assumption of is what is on the stack. Okay, so what is on the stack can be assumed, and that's basically the way for a caller and a callee to communicate. So that means, from the perspective of the callee, the only thing it knows, okay, the only thing it knows is whatever the stack pointer points to is the return address. That's the only thing it can assume. Alright, so assuming this is the only thing that the callee does know, that means it has to go to that location, go to the location that the stack pointer, which is register D, is pointing to, retrieve that, okay, and then put it into register A, and then declare that location to be useless at this point because it is now quote-unquote consumed. Okay, and Jonathan is correct. We need a pop, and what Matty typed here just need to be the opposite direction. So Matty, what is the opposite of stda? No, we are not storing. We are not storing to RAM. We are trying to retrieve something from RAM. Yep, Richard is right. And yep, okay. Yeah, I think Matty knows the answer. Just kind of not know what opcode or what is the mnemonic to represent it. So the answer is right. Okay, we just need to LDAD. Now, do we have to stick with register A? Nope. We can use register B. We can use register C. Whatever register you want to use other than register D is going to be okay. Not a problem. But we also have to remember to do the increment D because we have now just quote unquote consumed the byte that we have just read from. Because who else needs to know about the return address? Nobody else. Okay, this is the only instant of time where that value is actually useful to us. So once we have put it into register C, and then we know that later on we're going to use register C to tell us where to continue execution, nobody else needs access to that location anymore. So we can deallocate that byte. Now, when I say deallocating, I'm simply moving the bookmark past one page and say, hey, everything before this page is up, can be reused, okay, can be recycled. That's all it means. So when we get to the JMPC instruction, it would continue execution, at the label of first call of F returns here. So now we have to call again, and what are we gonna do? No, it goes from 255 back to 0 because it's 0 at this point. After this, it is 255, and then after this, it's back to 0. Yep. Okay, but it's good to kind of confirm that. Okay, it's a good observation, so it's good to type up your observation so that I can take a look and see if it is just off by 1 in this case. Okay, but the concept, I think you got the concept. It's just that when you do the counting, you're forgetting that we started with 0 in this case. All right, so what about the second call? Same thing, right? So as much as I don't really like to copy and paste, I'm gonna do it. But when we copy and paste, we have to be careful because the label that is marking where we need to go back to really should not be this anymore, right? Because if we were using the same label, then it will go back to this point over and over again. It will never go forward. So what we need is a new label that we need to define right after the JMPF, and we'll call this second call to F returns here. So we have second here, and this also needs to be second. This is why copy and paste can be very dangerous, because if you copy and paste a block of code and you modify some of the copied code but not the rest, the code can still be syntactically correct, but it would actually be wrong, because in this case, if I change only one of the labels, it's not going to work. Oh, right. Okay, let me move it up like that. Okay, there we go. So the second call is about the same thing. We allocate 1 byte from the stack. We use the label second call to F returns here, which is defined here, which is basically the address of the halt instruction. We put it into register A first because that's the only way we can store something into what register D is pointing to, and then we continue execution in the subroutine. The subroutine says, okay, I'm just going to go back to the stack, retrieve the previous item that was stored on the stack, which turns out to be the return address called return, oh, typo here, second call of F returns here. So this will basically load that label into register C, increment D, so D would be back to 0 at this point, and then JMPC is going to put whatever A has, C in this case, whatever register C has into the program counter itself, since register C is going to have the value of this label, which is the address of the halt instruction. So when we execute the jump instruction, it will continue execution at the halt instruction here. Yes, there is a lab today. That's why I talk about this stuff here, because this is what you'll be doing in your lab. Alright, so this looks pretty abstract. There's a lot of, just mumbo jumbo in here. So the question is, can we visualize the execution of this code? And the answer is, yes, we can. Okay. Unfortunately, I haven't really fixed my script to automate everything yet. It was working before, and it's not working anymore. I don't think it has to do with two-factor authentication, because it only makes use of Google Drive. So I have to figure out why it is not working at this point. But that's okay, because I can always do it the long way. There's always a second way of doing something. So we go back to the shared folder into processor as a subfolder. So this is also exactly what you can do. I know I'm doing this pretty quickly, but when you watch the video, you can kind of just take screenshots and then type some notes on the side, so that you can have your own concise instruction of how to do this. All right, so the first thing we need to do, the only spreadsheet we need is actually just the assembler in this case. So we get to the assembler, we get to source, and one thing you probably want to remember to do all the time is when you want to type in your own program, just going to clear out your column A. So I'm just pressing the delete key even though it's already empty. It doesn't really do any harm. So empty, so I have just emptied out the entire column A. Then you can use a text editor, and then just copy and paste the content from the text editor, like this entire program, into the first cell of column A. Remember, don't double click. If you see the blinky cursor in the cell, that won't work. Okay, so you have to make sure you're not looking at the blinky cursor. And then we can use column B to see if there are any errors. Okay, there are no errors here. Then you click on RAM file, and then we confirm that it's not reporting an error in the first cell. And then we go to File, Download, and I use CSV, for the RAM file itself. And I typically like to save it to a place where I know where to find it. So in my case, I put it into my temp folder. That's a Linux thing. I think Mac OS may have a temp folder too, but in Windows, you might want to designate a place to save your file. And we'll just call this call return. Okay, press enter key. Now the CSV is saved. And then next we need to collect the trace. Okay, so to collect the trace, you kind of have to use the command line version of Logisim. There's no easy way around it, unfortunately. I'm just looking for the one. They're all about the same. I'm looking for a terminal where the size of the text is reasonable. I think this one is fine. There we go. All right, so the full command of doing this is java-jar, and then you have to give it the path, which is to specify where it can find logisim310.jar. So we have kind of talked about this before. Actually, I talked about this in week 1 of the entire class. So we get to the folder. It's under, oh, okay, this is where it's supposed to go. Logisim 310.jar. There we go. Alright, so if I just press the enter key right now, it just starts up Logisim, which is not what I want to do because I want it to run the simulator itself. So the second thing we need to supply is where to find processor 0004.circ. So documents, CISP310. I put it into a subfolder over here, and the name of the file is processor 0004.circ. So if I press the enter key right now, it will start up Logisim and will load the processor in Logisim, but it will be in GUI mode, which is also not what I want. So now we need to specify -tty, which is teletype, the abbreviation of teletype, which basically just says don't get into GUI mode and instead generate the output in a table form. So -tty table is they need to be right next to each other. You have to type -tty and then table. And then this will basically run Logisim in a non-interactive mode, and whatever thing you do, it's going to crank out the output. But then we have to specify what program to load into RAM. So that's the next step, which is a -load. And then you have to specify the path to the CSV file that we have just saved. Now in my case, I put it into the temp folder and I call it callret.csv. And at this point, I think this is all we need to do. But the output is going to be just a bunch of zeros and ones generated to the console, which is the command line interface. So in Windows, this is probably your CMD or PowerShell, and then in Linux, this is this is what you see in Linux typically. Mac OS 10 probably about the same as Linux. All right. Oh, my video. I can turn that off. There we go. All right. All right. So I can also, yeah, I think this will work. All right. So if I press the enter key right now, just get a bunch of zeros and ones. Not helpful, right? So what we need to do is to use the greater than symbol, which is called the redirect, operator or redirect symbol, and we will capture the output. I typically put it into the same file name, but with a different extension of TSV, tab separated value, because this file really is tab separated in terms of how the values are specified. So this is how you usually do it. Press the enter key, and you won't see anything in the console anymore because all the output are now stored in wherever I redirect the output to. So callRed.tsv will contain what you previously saw as the output of this file. Then we go back to the assembler, and then we switch to trace raw data as a tab, and this is where we do all the import. So we go to file, we click import, and then it gives you an option to upload. So we click upload, specify where the file is supposed to go. So this one is in temp callRed.tsv. So don't confuse the CSV versus the TSV. So the TSV, okay, one easy way to remember is T for trace, even though it's not. Okay. So if you ever have a question of should I use the TSV or the CSV, if it's the trace, use the TSV. All right, so we don't want to create a new spreadsheet. We want to replace the current sheet, and we do not want to detect automatically. We want to specify tab, and most importantly, we want to turn off convert text to numbers, dates, and formulas, because otherwise the script is not going to work. And then we press import data. So now you just wait for the progress bar to be done. Now that is really fast. I'm impressed. And now we get to analysis. This is where it is going to be helpful. Okay, column A is telling us where are we getting instructions to execute. We're getting instruction from location 0, 0. And then the other columns will tell you what is being done when that instruction executes. So in this case, at location 0, 0, it shows nothing. So it's basically telling you we are not doing anything with this instruction. Are you surprised? It's a no op instruction, no operation. And then at location 1, it shows that we are reading from RAM. Okay, yeah, we are reading from location 0 in RAM, and it has a content of 9F. So that's actually a leftover thing. Okay, so you don't really have to be too concerned about it. And then we continue execution at location 06. How did we jump from 01 to location 06? The Jmpa main is what did this. Okay, so we continue execution at location 06. And what it did was to initialize register D to 0, 0. That's our sub DD instruction. Okay, that's how we initialize the stack pointer. So when you go through this, okay, of particular interest to us for this class and also for this lab is how we use the stack. This is how we store the return address on the stack. Okay, and if I go back to the code, let me go back to this code here. What you see here in the spreadsheet is corresponding to this instruction here. This is how we store the return address onto the stack. Now, how do we utilize it? Well, we first have to continue execution at the subroutine. This is at the subroutine F. And the first thing, the only useful thing it did is to retrieve that, and it will put it into register C. So this part here is corresponding to this instruction over here on line 7. So I'm not going to complete the whole thing because we are running out of time, but the trace shows you everything. Okay, it shows you the entire program's execution and what it did to reading RAM and writing to RAM and how the registers are being changed. So columns B, C, and D are really kind of useful, especially when you look at locations of FF and 00, and also changes to register D, because right here, register D went from FF back to 00 because we increment the stack pointer over here. So this is how this is one step toward the visualization of the operations that we are performing on the stack. It's really difficult to um, use a static medium to show this because it's really kind of an animation thing, because we can reuse the same location of RAM over and over again. So it's really kind of difficult to show you, okay, this is a static picture that shows you what is going on. That's not going to work. So what you need to do is to really kind of go through this, the whole sequence. I know there are a lot of empty rows over here. That's because my script is not working. I'm going to fix it so that you guys can use it too. But if you just ignore all the empty rows, okay, and just kind of focus on, when there are actual entries over here, most of these are useful, especially when the register is changed. It is always significant. Whenever a location of RAM is changed, it is always significant. Whenever you read from a location that corresponds to the stack, which is the high addresses, it is always significant. So that's kind of a tool, for you to kind of help you understand how this particular program works. And this program, in return, is really corresponding to the C code. Okay, C++. I keep using C because it really is just C without using the extra features in C++. So that's why I keep referring to this code as C code. But to make sure that you guys understand, yes, this is also stuff that you should understand too, I'm going to use C++. So this really just corresponds to the C++ code that we talked about in class today. Not this one, but the module right here. Alright, so I'm done with lecture. Yes, I did use some extra time, so I'm going to give you guys back that extra time. I'll postpone the due date to 16 minutes past the usual normal 120 deadline. But this is really kind of important stuff, and I'm going to design some activities for you guys to do before we meet again next Tuesday. And then on Thursday, maybe on and off, I can get onto Discord to answer some questions. So if you want to kind of keep the engine warm, I'll give you guys something to do. I'll be going to have to do the upload to trace the assignment. I think the assignment does not specifically ask you to do the trace. I could be wrong. Let me take a look at the lab here. Okay, so this is the lab. So I'm just going to quickly glance through the questions here. Which of the following instruction mnemonic retrieves but does not remove an item from the stack to register A? So this is definitely not about tracing. Which of the following instruction mnemonic is useful to allocate space on the stack? That is also not going to be a trace type of question. This one. What does this instruction do? So that's also not a trace type instruction question. This is question number 4. How many bytes are used on stack? So this one, if you use the trace, it might be helpful because you can actually track down the stack pointer and see how far it went as it goes lower and lower. This one, by the way, corresponds to I think it's a recursive subroutine. But you don't even need to know what type of subroutine it corresponds to. I can talk about this on Thursday. Okay, so I can design something around this one. But the important part of this one is you can run it. Okay, it starts with a no-op instruction, so you can actually just follow what I did to run it with a trace, and then when you look at the trace, you can also see how register D is changing over time. And you basically have to say, okay, how low did the stack pointer go? Because that will tell you the number of bytes being utilized by this particular program. And then you'll be able to answer the question of, let's see, where's the question? Okay, so here's the question of, up to how many bytes are used on stack during the following program that calls a recursive subroutine. So The easiest way to do this is really just to run it, just like what I did with with the TTP simulator, and then collect the trace, and then upload the trace to the analyzer, have it analyzed, and then track down how register D changes over time. So that's one way to do it. So the other way to do it, which is not what I would recommend you guys to do it before you got the answer, using the more obvious way, is to analyze the code. Okay, figure out what the code is really trying to do, what is the nature of the recursive subroutine, and then you can also answer the question that way. But once again, that's a very time consuming method, and some of you may not feel comfortable doing it that way, so don't feel pushed to do it in that particular way. And then here's the last question. And I think this one is not even a question. This one is really just a point to make at the very end here. So there you go. So I hope your question is answered, Matty. So you don't have to upload the trace as a part of the assignment, but using the trace can be helpful to answer some of the questions in the lab today. So is that good? All right. So Lifo is the key of this lab, and you can start now. I have to readjust the due date. That's going to be 1:40. I'll give you guys up to 1:45 p.m. I don't think it will take that long. I think most of you will be done in way before that time, but I'm just going to give you guys up to that time just in case. Yeah, if you're not running Linux, it will still be working. You just have to find out how to do the same thing in Windows. So for the rest of you, if you want to kind of break off and start doing the lab, you can do so. But if you are using Windows and you are wondering how to do that, I can give you some pointers, okay? Because I'm not very well versed in using Windows, but I can show you what it might look like in Windows. Alright, so here's the command in Linux. So for the most part, you can use the same structure. It's just that all the / should be / in Windows. And then depending on where you put your files, those locations would also be different. Alright, so let's start with this one over here. There's no such thing as a home folder. The tilde symbol doesn't work as a home folder. So, if you want to refer to home folder in Windows, there's a specific way to do it. You can actually do a Google search and find out, how to specify the home folder. I'm going to do that right here. Home folder in Windows. There we go. Oh, sure. Absolutely. I think it's %user%, but I could be wrong. So I'm just gonna double check here. Yeah, I think this works too. Just C:\users / and then whatever username you have. But there's a better way to do it. I know there's a shortcut or there's an abbreviation to refer to the home folder in Windows. So let me look up Windows paths. And this is from Microsoft. I think I put this link in the text channel in previous classes already. So I'm putting it today into today's lecture. Let's see. Pretty sure there's a way to specify the home folder, but that's C#. All right. Yep, there we go. So it's home dir, home drive, home path. There we go. Yeah, so unless you're on a different drive or for strange reasons, home path typically would work, unless your command line prompt is on a different drive. So to go back to the command that I had here, so basically in Windows you have to replace it with a percent symbol, and a user path percent here, and all the forward slashes need to become backward slashes. So everything becomes backward slash, and where you put your actual file kind of changes how what this path is going to look like. But basically, everywhere you see the tilde symbol, you have to replace it with percent user path percent. And let me just double check. Home path, not user. Okay, so my bad. Over here. I probably should have just started up my virtual machine to try out all of these things. Yeah, I can paste it, but I'm not really sure how helpful it's going to be because it depends on where you put your files. So this is based on where I put my files, but if you put your files into a different type of folder structure, you're going to have to change a bunch of this. And this part also depends on where you put your CSV. So you can say home path percent and a backslash, wherever you want to specify that. So just a whole bunch of home path. Now if all of these files are in the same folder where your command line interface is located, it's called a working directory, then you don't need all of this stuff here. Okay, if your logicsim jar and your processor circ and along with the other two circ files, along with your CSV and your TSV file, if you want to put everything into one folder and your working directory is that folder, you can just refer to the names of the files. So that would be the easiest way to do it. Yeah, you can also use WSL. WSL is Windows Subsystem for Linux, so that works pretty well too. So I'm putting this into there we go. So once again, you probably need to make some heavy-duty changes depending on where your files are located. But for the most part, that is the approach. Okay. Yeah, the problem with using WSL is you will also have to install Java within the Linux in WSL. So that can be you kind of need to know what command to use to install Java in that case. One other thing you can try is called Cygwin, Cygwin. So Cygwin is a way to use a lot of the Unix type of command line interface stuff, but within Windows. So that's possible. Yeah, VirtualBox is also good, but it's not directly supported by Microsoft. But it works. It works really well. Yep. All right. So I'm gonna stop the lecture at this point. I don't even know how many people are still on the voice channel. So I'm gonna stop recording. If you guys have any additional questions, I will answer those questions. I'll still be online until the end of the lab. All right. So I'm gonna stop the voice channel now.